Hi, everyone. This is Eli Lubarov, founder and CEO of Desmos, and I'm here with our fifth ever webinar coming off of an incredibly exciting week. So for those of you who ran into us at NCTM in Denver, thank you so much. It was a blast for us. That happy hour was great fun, and it was just so great to be able to hang out with 8,000 teachers in the Mile High City, especially once it stopped snowing. My plan for today was to do a recapitulation of a presentation that I gave alongside Patrick Venebush of Illuminations at NCTM formerly and now at Discovery, the head of math. We set this up and took people through examples of using Desmos along with the Illuminations content. And for those of you who have spoken with us, you know that we're extremely into project-based learning in general, and that we have a few go-to resources for project-based learning. Dan Meyer's blog, the Mathlicious team, and the Illuminations website are three of our favorites. And so this is an example of taking you through some of the Illuminations projects and using them along with Desmos. So a little bit of logistics. As always, we're going to have someone, in this case, Jenny, our lead designer on Twitter, answering any questions you guys have. So as we're going, let me know if you want me to speed up or slow down, or if you have any questions about what we're doing. You just tweet at Desmos. That's @DESMOS, my shirt, but backwards. So I'm going to start by sharing my screen and just showing you how you can use Desmos alongside Illuminations in your classroom for some really fun project-based assignments. So here you should be able to see my screen now. Let me know if this looks right. Great. And so, as I said, this was alongside Patrick Venebush of Discovery Education. The talk that we gave was entitled Powerful Online Tools Promote Powerful Mathematics. And I'm going to take you through just two pieces. It was an hour and a quarter. The goal for this is to keep it to about 20 minutes. So we're going to skip over the intro activity that we did. It was great fun. Skip over the introduction to Desmos. If you have any questions about that, you can always email us, calculator@desmos.com, and go straight into the first of these problems. So this one is right off of the Illuminations website, and it's called Successive Discounts. And the premise of this problem is that you receive a coupon for $5 off a pair of jeans in the mail. When you arrive at the store, you find that all jeans are 25% off. If the jeans were marked at $36, how much will you pay before tax? And we decided to turn this into an exploratory problem. And so I'm going to pull up Desmos. You should be able to see my screen. I'm going to first go over to options and put it in projector mode. In addition to being great for seeing Desmos at the back of the classroom, turns out this is the best way to see it on a webinar. And we're going to start with a slightly simpler problem, which is we're going to say these jeans were $36. What would it cost if we just had a $5 discount? Turns out Desmos can do computations if you want it to. So I'm going to write just 36 minus 5, not a very hard one. We get $31. The other possible discount that we had was 25% off. And for that one, it would be 36 times, and I'm going to do this as 1 minus 25%, which is the same as 25 divided by 100. For those of you watching who haven't played around with Desmos, I'm just typing this in as I go. So to get this divided by, this divided by sign, I just did a /. And here we can see it's a better deal to take 25% off than to take $5 off. But this isn't very general. It's not really making use of Desmos. So let's make it a little bit fancier. And we're going to change this to saying instead of taking $5 off this specific price, let's generalize this problem. Let's say we're going to say that the x-axis here is the price of the jeans before the discount. The output is going to be the price of the jeans after the discount, and so that'll be the y-axis. And we're going to turn these into function definitions so that we can do fun things with them. So now instead of saying that the price of a pair of jeans that cost $36 or 36 minus 5, we're going to say if the jeans cost X dollars, it's going to cost X minus 5. I'm going to define this as a function so that we can use it later. This is one of the tricks that not everyone finds on Desmos, but you can define functions. If you just type f of x equals x minus 5, we can now use f elsewhere, and we're going to use it all over the place. I'm going to do the same thing with this 25% discount. So instead of saying it's 36 now, I'm going to say it's X dollars coming in. How much does it cost going out? I'm going to call it G of X. And instead of being 36 times this, it's X times this. So it's 75% of X. Now this is all well and good, but we can't actually see very many interesting parts of this graph yet. So we have a couple options. I could zoom out, which I could do using my scroll wheel, and we get to see more. And that's probably the best thing to do here. I could also have gone over here, pressed Options, and then set the window manually. But for now, zooming out with my scroll wheel seems to get us a lot more information. So this specific problem that we were looking at was asking about a $36 pair of jeans. We can draw a vertical line to see where that lies on our graph by doing X equals 36. And in fact, we can start to see those same values that we had before. So we had $27 for G of X. You can see it's highlighted in blue. And we had $31 for F of X. So it's a better deal to do G of X than F of X. So quick pause. And I'm going to go back to the problem as it was described over on this tab. As always, interrupt us if you have questions. Jenny will ask me or try to answer them herself at Desmos. Here it was saying we received the coupon for $5 off and everything is 25% off. And so we're actually getting both of these discounts. But that brings up an interesting question. Does the order that we apply these discounts matter? Is it better to take off $5 and then 25% of what's left? Or should we take off 25% and then subtract $5? Well, it turns out that since we defined F and G as functions, we can try both of those and we'll be able to see very visually which is a better deal. So at this point, I turn to the audience. I can't do that now because it won't be quite synchronous enough, but I'm just going to go forward with it. And I'm going to try one and then the other. And the one I'm going to try first is the one where we first subtract $5 and then we take a 25% discount. So that means that I want to apply our F of X discount first and then apply the G of X discount. And the way we do that is doing G of F of X. And so here you can see it worked that we defined this function as F and G because then we can reference those later on and we can see what's happening. And so now this black line, it's cheaper than either of the others. That's what we expect because we're getting two discounts and not just one. But let's try the other order as well. Let's do the one where first we take a 25% discount and then we subtract $5. We take F of G of X. And at this point, it will be a perfect time to turn to your students and say, what do you notice about these lines? And I notice a few things about these lines. So one of them is that they're parallel. That was a surprise to me. It turns out that whichever order we do the discounts, one of them comes out to a fixed cost cheaper than the other one. And we'll figure out what that is. No matter how much it was, a $100 pair of jeans, if you do it in one order, you get a price. If you do it in the other order, you get a slightly cheaper price. But the difference is the same throughout. It's parallel lines, which is really interesting. And the other is that F of G of X is better. So if we first do the percentage discount and then the fixed discount, we end up paying less for our pair of jeans. And if you take a step back, that actually starts to make a little sense. Because if first you subtract $5 and then do a 25% discount, you're also discounting that $5. We're taking 25% of that $5 discount and throwing it away. And that's $1.25. And in fact, if we look at these closely, we'll see that the difference between them is always $1.25. So these lines are $1.25 apart. And the short answer is that if someone at the store asks you, would you rather apply the $5 discount or the 25% discount first, you're always better off doing the fixed discount as the second one you do so that you're not discounting your discount. So this is where we could have stopped this problem. In fact, we could have stopped it a long time ago, but with Desmos, it's way more fun to just keep exploring. And so in the presentation, we went one more step. And the one more step that we went was to generalize these. Desmos is really good at taking parameters like this $5 discount and turning it into something general. So instead of taking $5 off, let's take $8 off. And Desmos looks at this and it says, I don't know what A is. I bet it's a parameter. Let's turn it into a slider. Turn it into a slider. We can set it to 5, just like this. And so now it looks exactly the same, but now we can see what happens if it's a bigger or a smaller discount. What do we think is going to happen to these lines? Well, one of them is going to stay exactly the same. The purple line doesn't ever see A, but all of the others are going to move. And it's interesting to look at how they move. So the red one just moves down, which we expect. The black and the blue actually get further apart. It matters even more the order that you take the discount. And when that discount is 0, we see the lines all pile up in a way that we expect, because the f of x discount actually isn't a discount. So that's kind of fun. Let's generalize the other one too. Instead of saying that g of x is a 25% discount, let's make it a b% discount. So I'm going to do a new line. I'm going to type b equals 25. And here we can see what happens if we shrink that percentage. Well, in this case, the red line f of x doesn't change, but all of the other ones do. And again, you can see that they move further apart and they change angle, but it's really fun to see that, in fact, the purple, the black, and the blue are all parallel to each other. Really surprising insight. So here with Desmos, we were able to take this very simple problem of the order of discounts and turn it into a general problem, which let us explore how these parameters actually change the nature of this problem. So after this webinar, we'll be posting links to this graph, as well as the one that we use for the second activity. But that was the first activity that we did at this conference. Any questions about that? Remember to tweet at Desmos, and we will answer them as they go. Oh, we have one question here. Someone said, the B slider, I didn't press add slider. What did I do? Well, the answer there is that you can either press add slider and we make one for you, or you can just type in a number and we'll turn it into a slider. We'll detect that you probably meant a slider. And this way you can do precise numbers instead of just having it start at 1 and go between -10 and 10. So you can make something that's even bigger and still a slider. Good question. All right, going back to Illuminations. The second problem that we did was super fun, and it's going to be a lot harder to do as a webinar than it was in person. But I took some of the data from it, and so we're going to be able to do it. And this one was an example of data collection and then performing a regression using Desmos. For those of you listening, the warning is that we don't actually do regressions, but what we do is almost as cool, and we thought this would be a great opportunity to show how to use tables alongside functions in Desmos. So this problem went, we handed out a whole bunch of balloons and measuring tapes, and the challenge was to blow into a balloon, measure the circumference after each breath, write them down in a table, and then we were going to try to figure out the pattern of how the breaths related to the circumference of the balloon. So 5-minute break for everyone to blow up their balloons and a whole bunch of people to pop them. And then we get right into the data collection. So this was the data we collected from one group for the inches of circumference of a balloon versus the number of breaths. I'm going to go back to Desmos. I'm going to clear this. Actually, first I'm going to save this. So we'll call this Gene's discount. I'm going to save this so that I can send it out. And then I'm going to press clear, this new blank graph, and start working on this table of data. So if you press this little slide out button here, and then press table, this lets us do a new input type, which is a table of data. And here I'm just going to fill it in with the data that we collected, which was that we had 1 breath, 2 breath, 3, 4, 5, and 6 different breaths. I'm navigating this just using my arrow keys. After the first breath, the balloon was 19 inches in circumference. After the second, it was 24. After the third, it was 27.5. And then it was 30, and then 32.5, and finally 35.5. So all well and good, we've got a whole bunch of data in a table. We can't see it anywhere on the graph. That's because our screen is wrong. So we could pan around until we found it. There's our data. We could zoom out. But in this case, I think we're going to want to set a custom window. So the way that we do that is we click over here into the options, set the window for X. Let's go from maybe, for X, let's go from -2 up through 8. And for Y, let's go from -5 up through 40. So now we can see the data a little bit better. At this point, someone called out from the audience and they said, isn't there one more data point, which is at 0? We know that the circumference is 0. So let's add that data point. And now we can also see this one more. And then the challenge was to try to figure out a curve that fits this data. So we asked what curve would work. If you guys have any suggestions, feel free to tweet them at us. But I'm going to start with the first suggestion that we got, which was that this looked like a square root function. Just to give us a little more real estate, I'm going to minimize the keypad here. So we could try a square root function. That doesn't look good because we probably wanted some constant in advance of it. And so I'm going to use sliders again. And I'm going to say maybe it was y equals a times the square root of x. Open this up. I'm going to slide it. I need to slide it a little further. And so if you click on the endpoint here, you can set the domain of this slider. We'll go from 0 to maybe 25. And let's keep going until it looks like it's close. So that's not bad. Maybe it's something like 15.4 times the square root of x. So then we asked for another idea of a function, and someone suggested a cube root. So let's try that as well. If we do something like y equals b times, and in case you haven't seen this yet, we recently added a cube root button. So if you open up the keypad, press more, and then press this cube root button, you get the cube root. So we'll do b times the cube root of x. Have to turn that one into a slider also. Here's our cube root function. Let's try sliding that up. And again, we're going to have to make it a little bit bigger, so we'll go up through 25. And that looks like a much better fit. So this is a way we could have done it visually. I'm going to actually turn off this square root function for now. But how can we use our table to check it? Well, one of the secrets of tables is that you can give them multiple columns. And so in addition to x and y, we could make a third column. And you can even make a column that is a function of the other columns in the table. So we could, for example, do something like x plus y if we wanted, and it'll fill it in for us. That's not very useful. In this case, we want to know how far our guess function was from our data. And so we could do a column that looks like y minus f of x. Uh-oh. I'm going to have to define these as functions, aren't I? F of x, g of x. Here is our y minus f of x. We actually thought the cube root was closer, so I'm going to do g of x. And to make it a little bit more visual, I'm going to connect these dots. And to make it a little bit more accurate, I am going to square it, because that's what we're looking for, is to minimize the square of the distance. So here we have this new data that shows us the difference between our curve and our dots, and it's actually the square of the distance. And just to see how tables work, what if we change this b? Because what we want to do is minimize that. We can see, oh, that's a pretty bad b. That's also a pretty bad b. And the best one is down here. And just in case we wanted to see, was the cube root a better idea to use than the square root? Let's add one more column, which is our square root. So it's going to look exactly the same. It'll be y minus now f of x squared. I'm going to turn off our g. I'm going to turn on our f. And I'm going to see, and going back here, I'm going to connect these dots again, and let's make them maybe green just so that we have another color. And we're going to see how good can we make the square root. Can we adjust a so that it looks as small as those purple dots? And visually, it looks like we can. it looks like our best fit was in fact the cube root function, which was this g of x. So this is kind of a way that you can fake regressions, but actually in a way that's even more instructive. You get to show the students and have the students explore what the parameters do without just having the answer get spit out in their face. So this was the second problem that we did. One other question that we might have would be to look through, question?
Can you sum the values in the list?
Can you sum the values in the list? That is an awesome question. And the answer is we cannot yet sum the values in the list, but one of the big things we're working on is making it so you can export data from the table and do operations on it, like sums, for exactly this reason, because we're actually minimizing the sum of the squares, not just the individual squares. So this is visual, but it doesn't give you the final answer. So great question.
Can you turn one of those functions into a table on its own?
Can you turn one of these functions into a table on its own? You can. So to show that, I'm going to just open up a new tab so that we don't lose the work here. Go to desmos.com/calculator. I'm going to turn this into projector mode. And the question was, can you turn a function into a table? So if you type something like y equals sine of x, if you go into edit mode, you get a few options. You can duplicate the function so that you can, for example, show transformations of it. You can delete it. You can also press this convert to table button, and we'll turn it into a table that shows the dots. Once you have it in table form, you can turn on and off the curve and on and off the dots. So this is just another way to look at the same function. If you want to change back, you can always press undo to get back your function. So here we had this regression, saw a whole bunch of fun ways that we can explore this data. One more question you could start to ask is, if we zoom in here, we can look, even when we were really close, our last data point was way off. And in fact, if we look at this table, we have this kind of surprising result that the differences are shrinking. We go 5, and then 3.5, and then 2.5, and then 2.5, and then at the end 3. And you could start to have a conversation about what happened on this 6th blow where we got data that didn't really fit our model. Does it matter? Should we trash the model? Or is it something else? So we had a fun conversation about that, about was it measurement area? Did the whoever blew up this balloon and measure it tilt the ruler when they were doing this part, or blow a little harder on the last one? Or was it actually a property of physics? So for example, balloon's elasticity decreases as it grows bigger. So it's easier to blow it up the bigger that it gets. Maybe that was the factor that we saw here. But definitely gives you a fodder for conversation, which is part of why we love these Illuminations problems so much, is that they're open-ended and just really rich in kind of information and questions that you can ask coming out of them. So I'm going to share this graph as well. If you go to desmos.com/concepts, we have one that is related to this. This is our experimental page of showing different ways of using Desmos that we've seen people do in the classroom. Under this modeling tab, we have an example of this table of data with residuals, with some explanation in it, so that you can poke around with that or modify it for whatever activity you're using. But with that, I think I'm going to wrap up this webinar with a huge thanks again to Patrick Venabush and Illuminations for their great resources, and to everyone who we saw at NCTM. And we'll see you again here in a couple weeks. Thanks so much.